Development length is denoted by LD, and it is the shortest length of a bar embedded in concrete for which the bar yield before the pull-out failure. And if the embedded length is less than LD, development length, in that case, is equal to LD, in that case bar yield but not pulled out of the concrete. But if the embedded length is less than LD, in that case bar will be pulled out of the concrete. So we can understand this in this way. For example, we have 3 cylinders and a bar of 16 mm diameter is embedded in these cylinders. For the first case, the embedded length is 300 mm. In the second case, the embedded length is 290 mm, and in the third case it is 280 mm. And for the first case, when we apply the load P, it fracture because of yielding at the face of this cube. And the area of bar AS is equal to 200 mm for 16 mm bar to square, and suppose Fy of this bar is 420. So the P, the load at which this fracture occurs, it is equal to actually AS Fy, the yield strength of the concrete times the area of bar. And while substituting these values, it will become 84 kilonewton. In the second case, again when we apply this load P, suppose it also fail at this point at the face of the cube and due to the yielding of the bar. Again in that case, the P will be equal to AS Fy, 200 times 420 is equal to 84 kilonewton. And for this case, for example, for this P, for this case when the embedded length is 280 mm, instead of failure at this face, this bar is pulled out of this cylinder. So when this bar is pulled out of this cylinder, in that case the stress in the bar is less than Fy. As it is not yielded, it means the stress in the bar is less than Fy. So the maximum load, or the load at which this bar is pulled out, will be AS times Fs, and 200 times, instead of 420 it will be less than 420. For example, it is equal to 350. So in that case the load will be less than 84 kilonewton. So at the lower load, the bar is pulled out of the concrete and it is not yielded when the embedded length is 280 mm. When we increase by 10 mm, it is yielded but not pulled out. When we further increase the embedded length, the case is again same. The bar is yielded but not pulled out. So the capacity or the load at which this failure occurs, it is 84 kilonewton and it is 84 kilonewton. And here the failure will be at lower load. So this embedded length 290 is our development length. This is the minimum length at which our required failure occurs. The yielding of the bar is occurred but not a pull out, because when a pull out failure occurs, the full strength of the bar is not utilized. So we need to utilize the full strength of bar. So for an ideal design, at failure the stress in the bar should be equal to Fy, and we can achieve this at 290 mm. And if we go on increasing the development length, it will not give us any benefit. So this minimum length, embedded length, at which we get our desired result is termed as the development length. So that's why we say that it is the shortest length at which the yielding of the bar occurs before the pull out. Okay. So at that stage, for the design, for the ideal design, as we said earlier, so the load will be equal to AS Fy, the yield strength of the bar times the area of the bar, and the resistive load will be equal to the average bond stress multiplied by the surface area of the bar. Here the surface area of the bar will be equal to the perimeter of the bar times the development length. So when we rearrange this equation, so we will get this LD is equal to diameter of bar times Fy divided by 4 times bond strength, average bond strength. So this LD is our required development length to cause the yielding of this bar. So to get the maximum benefit, embedded length should be equal or more than this value. Development length in tension is more than the compression. The required development length in tension is more than the required development length in compression. It is because of the two reasons. The first reason is, in case of bar under tension, it is subjected to in and out bond stress. For example, if the bond stress in the bar is like this, in that case the average value will be this one. If the bond stress is like this, in that case the average value will be, the average value, overall average value of the bond stress will reduce because of this in and out mechanism. And in case of bar, when it is under tension, the concrete around it will crack like this, and each segment of this beam or cylinder will act as a separate portion, and for each portion there will be in and out mechanism for the bond stress, and as a result the average bond strength will be reduced. So average bond strength, when the average bond strength is reduced, then the required development length will be increased, as we have seen that the relation between LD and average bond strength is inverse relation, 4 times mu. So mu is in denominator, so there is a inverse relation between development length and bond stress. Similarly, the second reason why the required length in tension is more than that of compression is that in case of compression there is end bearing as well as the bond stress that transfer the load from bar to the concrete. For example, if we have a cylinder and a steel bar is embedded inside it, when we apply the load, so this load will be transferred to the concrete by two mechanisms: friction at the side of this bar, at the surface area of the bar, and the end bearing. So this P will be equal to bond strength multiplied by the surface area plus the end bearing, which will be equal to 0.85 Fc prime area of bar end bearing. So here the load will be resisted by these two components instead of only this bond stress. That's why the required development length is reduced in case of compression.